I am looking right at you, sitting there at your lab
Oh,
bench.
absolutely.
It's week 2 of your first year robotics class. And I know the safety waivers are signed, the syllabus is totally memorized, and I know exactly what you've been up to in your dorm room.
Probably staying up way too late.
Exactly. You've successfully wired up your very first Raspberry Pi. You've, downloaded an open weights large language model. You actually got it running locally. And you've even knocked out some introductory CAD models for custom brackets. Your imagination is just completely running wild.
The energy in the room during week 2 is, honestly, it's always incredible. You have all these disparate ingredients, right? The silicon, the motors, the code, and you were just itching to get your hands dirty on that 2-year capstone project.
You want in, I get it. But right now, you're staring at this pile of hardware and, well, a whole lot of ambition. So today is the day we transition from reading the syllabus to cutting into the absolute theoretical meat of your curriculum.
Because your instructors didn't just pick any random, off-the-shelf software to govern your capstone.
Right. They chose the Qwen-Robot Suite. And we have a stack of 3 incredibly dense technical papers for this deep dive. They detail the ecosystem you're going to spend the next 2 years wrestling with, which are Qwen-Robot Manip, Qwen-Robot Nav, and Qwen-Robot World.
Yeah, we are going to treat this as a masterclass on the 3 foundational pillars of embodied AI. We aren't just looking at software updates here. We're looking at the actual architecture of how a machine interacts with reality.
We've got a really clear roadmap for you today. Pillar number 1 is manipulation, which is basically how the robot uses its hands.
Right.
Pillar number 2 is navigation. That's how the robot moves its legs or wheels through space and manages its memory. And then pillar number 3 is world modeling.
Which is how the robot imagines and simulates the physics of the real world before it ever moves a muscle.
Historically, those 3 pillars were, entirely segregated, weren't they?
Oh, totally. The manipulation team didn't talk to the navigation team,
Well-
and the simulation team lived in their own completely virtual bubble. The breakthrough of the Qwen suite is unifying all 3 of those through a single shared interface.
And that interface is something you use every single day. It's just natural language. But, well, we are getting ahead of ourselves. You have your Raspberry Pi sitting there. How do we get that pile of metal to actually do something complex?
Yeah, that's the big question.
Because you already know you can't just write millions of lines of hard-coded if-then statements. If the cup slips 2 millimeters to the left, your Python script fails.
It crashes entirely.
Yeah.
You need a system that genuinely understands the physical world. Let's start with the hands, which brings us to the first paper, Qwen-Robot Manip.
Okay, let's get into it.
The researchers state their foundational philosophy for this model right up front. It's alignment first, then scale.
Alignment first, then scale. Okay.
Right. And to grasp what that actually means for your lab work, we have to look under the hood at the architecture. Qwen-Robot Manip is a vision language action model, or a VLA.
A VLA. So we take the vision language part, the AI's ability to, look through a camera lens and semantically understand that it's looking at a red cup on a brown table, and we bolt an action module onto it.
That is the core idea, yeah. It couples a QuenVL backbone, which handles all the visual and semantic reasoning, with a flow-matching diffusion transformer.
A DIT.
Exactly, often abbreviated as DIT. That DIT serves as the action head. It's solely responsible for continuous motor control.
Okay, I'm going to stop you right there because flow matching diffusion transformer sounds like absolute engineering word soup.
It really does.
I mean, I know transformers run language models, right? And diffusion is what those AI art generators use to turn static into pictures. But how does an image-generating architecture physically move a robotic arm?
It requires a massive shift in how you think about generation. So in an AI image generator, the model takes random static and iteratively refines it until it forms a picture of, say, a cat.
Right.
In a robotic diffusion model, it takes random noise and refines it into a continuous trajectory of motor commands.
Wait, really? It treats motor commands like pixels?
Sort of, yeah. And the flow matching part is a specific mathematical technique that makes this process vastly more efficient. Standard diffusion can wander. It takes a chaotic, kind of winding path to reach the final image.
It takes too long.
Way too long for robotics. Flow matching calculates the most direct, straight-line vector field from the noise to the target action. It allows the robot to generate smooth, precise, real-time motor trajectories without needing, a supercomputer to process every single millimeter of movement.
So the vision backbone says, I see the red cup. The user wants me to grab it. And the flow matching DIT calculates the absolute straightest mathematical path to translate that intention into physical joint movements.
You got it. But joining those two systems together creates a massive internal conflict for the neural network.
I was actually just thinking about that. Because if I take a massive language model, something trained on all of Wikipedia, capable of writing poetry and doing logic puzzles, and I suddenly force-feed it millions of data points about joint angles, motor torques, and grip pressure,
It's going to struggle.
doesn't it just lose its mind? I mean, if I spent 12 hours a day solely practicing how to juggle, I feel like my ability to do advanced calculus would start slipping. Doesn't the pressure to act like a robot destroy its ability to understand normal language?
You are describing catastrophic forgetting.
Catastrophic forgetting.
Yes, and it is the absolute bane of embodied AI. If they trained this model naively, the sheer mathematical weight of learning continuous motor control would absolutely overwrite its generalized cognitive abilities.
So how did they stop that?
They solved this using a technique called dual-stream co-training.
Dual stream. So they are running two separate rivers of data into the model simultaneously.
Exactly. They feed a VLA stream, which is the purely robotic physical manipulation data alongside a VLM stream. And the VLM stream is standard vision language data, like visual QA or general internet text.
Okay, so it's doing both at once.
Yes. And the key to this entire architecture surviving is the ratio. They maintain a strict 9-to-1 ratio, 9 batches of robot data to 1 batch of general reasoning data.
Wait, what? 9-to-1? Why not half and half, just to be safe?
Because physical manipulation is incredibly complex to learn. You need the bulk of the computational weight focused on contact dynamics, friction, spatial orientation.
That makes sense.
But that 10% of pure reasoning data acts as a cognitive anchor. By constantly whispering general knowledge into the model's ear while it learns to turn a wrench, it prevents the higher-level semantic pathways from degrading.
Wow. That is a huge relief for anyone building their capstone, because it means when you type a command into your robot, you aren't talking to a dumb motor controller.
Not at all.
You are talking to a system that retains the generalized intelligence of the internet, but happens to have a black belt in physical manipulation. And honestly, it is going to need that black belt, because the hardware you all use in the student lab is a chaotic mess.
Oh, the hardware fragmentation in robotics is severe. And that brings us to the scale of the data. Qwen-Robot Manip was trained on 38,100 hours of manipulation data.
Which is over 4 solid years of non-stop robotic movement.
Yeah, the volume is impressive, but the source of the data is the real hurdle here. That data comes from 15 entirely different physical platforms.
Wait, 15 different types of robots?
Yes.
So you've got data from like a massive heavy-duty industrial arm, data from a tiny desktop educational robot, data from an arm with a parallel jaw gripper, and maybe data from a 3-fingered dexterous hand.
Exactly.
How does the AI make sense of that? It's like trying to teach a teenager to drive by forcing them to watch a split-screen video of a Honda Civic, a John Deere tractor, a motorcycle, and a forklift all at the same time. The steering mechanisms are completely different. The math just wouldn't align.
It wouldn't. In robotics, we call this the Tower of Babel problem. Every hardware manufacturer speaks a different mathematical language.
Right.
An Aloha arm might have 6 degrees of freedom, while a Franca arm has 7. If you just dump raw joint angles into the neural network, the math crashes. The model gets confused because the numbers mean completely different things depending on the robot.
So how did they build a universal translator for all this?
They develop what's called a canonical state action representation. Instead of feeding the model the raw, hardware-specific joint angles, they translate every single action from every single robot into a unified 80-dimensional mathematical space.
Okay, and an 80-dimensional space is going to lose a first-year student immediately. We need to ground this. What is the actual mechanism making these different robots speak the same language?
Well, they focus entirely on the end effector.
The hand of the robot.
Right, the hand. And they use something called camera frame delta pose parameterization.
Camera frame delta pose. Okay, so delta means change. Are they just measuring how much the hand moves relative to what the camera sees?
That is the core of it, yes. Think about the physical geometry of the arm itself. The shoulder, the elbow, the wrist. The researchers basically strip all of that away.
They just ignore the arm.
Exactly.
Yeah.
They only care about the hand's movement across the camera's field of view. If a massive industrial arm moves its hand 2 inches to the left to grab a mug, and a tiny plastic desktop arm moves its hand 2 inches to the left to grab the same mug, the physical joint angles are wildly different.
Yeah, obviously.
But the visual delta, the change in position relative to the camera, is mathematically identical.
Oh, wow. That is incredibly clever. By expressing actions purely as changes in visual position rather than mechanical joint rotations, visually similar motions become mathematically similar.
Precisely.
So the model learns the abstract concept of reaching for the mug, entirely independent of the hardware doing the reaching.
And we know this universal translation layer is the secret ingredient because they ran a really fascinating ablation study.
For the lab students, an ablation study is when you strip away a feature from your model just to see if it actually breaks. What happened when they took away this unified 80-dimensional mapping?
They tested the model on completely unseen tasks using a novel robot platform it had never trained on. With the unified action space intact, the robot succeeded 55% of the time.
Okay, 50%.
But when they removed that translation layer and just naively combined the raw data from the different robots, the success rate dropped to 7.5%.
7.5%. Without the translation layer, the robot is just blind guessing.
Exactly. It completely validates their philosophy alignment first, then scale. You can't just throw terabytes of chaotic hardware data at a model and expect it to learn. The data has to be semantically aligned.
And this leads to something that is going to directly impact your capstone project, especially dealing with your own terrible hardware in the lab.
A very real concern for students.
Oh, yeah. Let's say you 3D print a custom bracket for your robot arm, and because the print was slightly warped, the arm flexes a millimeter more than it should every time it moves.
Happens all the time.
Right. And you are running this off a Raspberry Pi. You do not have the compute power or the time to retrain a massive foundation model to understand your specific quirky bracket.
That is where in-context policy adaptation comes in. The model doesn't need to be retrained to understand your warped bracket. It uses its short-term memory to adapt on the fly.
Wait, how does that actually work mechanically? How does it fix the physical flex without a parameter update?
The model maintains a rolling window of its recent execution history. It constantly looks at the last few seconds of its own observation action pairs.
Okay.
Let's apply your warped bracket scenario. The model issues a command, move the hand 10 units to the left. Because of the flex in your 3D print, the visual feedback shows the hand only moved 8 units and it dipped slightly downward.
So it actually sees the mistake. It knows there's a discrepancy between the command and the reality.
Precisely. As it looks at that rolling window of history, it recognizes the pattern in context. It realizes every time I command 10 units left, my current physical embodiment only delivers 8 units, plus a downward droop.
Wow.
It implicitly identifies the unique physics of your specific hardware. So the next time it needs to move 10 units left, the model dynamically adjusts its command, perhaps outputting a signal for 12 units left and a slight upward tilt to compensate.
It corrects the physical error in real time.
Entirely through the prompt context.
It's like the rental car analogy.
Okay.
If you rent a car and the brakes are a little squishy, you don't go back to driver's ed to relearn how to drive. Your brain maintains a rolling window of the last few times you stepped on the pedal, recognizes the squish, and you naturally just start pressing the pedal a little earlier and a little harder.
That is exactly what the robot is doing, that cognitive adjustment. And because of this massive, aligned, adaptable training base, Qwen-Robot Manip starts displaying genuine emergent behaviors.
Emergent behaviors are like the holy grail of this field, right?
They are. These are complex, nuanced skills.
Right.
The model was never explicitly coded to perform. They just naturally precipitate from the scale and structure of the data.
The bimanual coordination example in the paper was stunning. The task was simply pour fries into plate.
Which sounds completely trivial to a human, but for a robot, it is a sequential nightmare.
The Qwen-Robot Manip model achieved a 30% success rate on this task, and 30% sounds mediocre until you read the chart and realize that every single baseline model they tested hit a flat 0%.
Right.
They couldn't even manage a single success. Why does a standard model fail so spectacularly at pouring fries?
Because standard models get trapped in local minima. If you only have one arm, you might try to swipe the fry box over or crush it to squeeze the fries out. To pour fries properly, you need asynchronous cooperative action between two distinct limbs.
Yeah.
The left arm has to reach out and apply just enough pressure to stabilize the fry box without crushing it. Then the right arm has to navigate around the left arm, open the flap, grip the edge, lift, tilt, and pour.
And the model learned to sequence those primitive actions flawlessly, purely from watching the data. But there is another emergent behavior that is going to save your grade when your professor comes to evaluate your capstone.
Ah, the autonomous retry behavior.
Yes, the failure recovery protocols. Because if you write a standard hard-coded Python script for a robot
Right.
and the gripper misses the object by half a centimeter, the script doesn't know.
No, it has no idea.
It just keeps running, it closes on empty air, moves an invisible object across the desk, and fails the task. Or worse, it throws a collision error and the whole system halts.
But this model relies on continuous visual feedback. In the paper, they document a specific task where the robot is sorting electronic components. On the first attempt, the robot reaches for the object, the gripper makes contact, but the angle is slightly off.
And the object slips.
It slips and falls back onto the table.
And what does the flow matching DIT do?
It doesn't crash. And it doesn't pretend it's holding the object. The visual backbone registers the discrepancy. The hand is empty. The object is still on the table. The model autonomously resets its trajectory and initiates a second attempt.
Incredible.
And in the specific documented instance, the object slips a second time.
So the model drops it twice.
Yes. But on the third attempt, the model recalculates its approach angle based on the previous slips, secures a solid grasp, and successfully places the electronic component in the bin.
The model didn't have a line of code saying, if grasp equals false, retry. It learned persistence. It learned that failure is just a state that requires a new action trajectory. So you have a robot that is dexterous, adaptable to bad hardware, and relentless.
It's a powerful combination.
But let's look at the limitations. Grabbing a dropped resistor off your lab bench is amazing. But what happens if that resistor bounces, rolls off the desk, and settles under a bookshelf on the complete opposite side of the lab?
Right. The hands are useless then.
Exactly. The most dexterous hand in the world is utterly useless if the robot doesn't know how to physically traverse the room to get there.
And that requires a total pivot, from localized manipulation to macro movement and spatial reasoning. We have to move from the hands to the legs, which brings us to the second paper in your stack, Qwen-Robot Nav.
We're transitioning from the hands to the eyes and legs. Now, my immediate assumption when reading about a navigation model was that I was going to see a completely new, bespoke neural network architecture built specifically for balancing, walking, or rolling.
That has been the traditional approach in the field, for sure, building highly specialized locomotive networks. But the Qwen team took a radically different path. They didn't invent a new architecture for navigation.
They didn't.
No. They took the existing Qwen 3VL backbone, the exact same class of vision language model we were just discussing, and fundamentally reframed the problem. They stopped treating navigation as a specialized motor control problem and reframed it as an observation context modeling problem.
Observation context modeling. Okay, let's translate that for the student. Think about how you navigate campus. When you are walking from your dorm to the robotics lab, you aren't consciously calculating the exact degree of flex in your knee joint for every single step.
It'd never get there if you did.
Right. Your brain splits the work into two tiers. The high-level part of your brain says, okay, the lab is in the engineering building, so first I need to cross the quad, then find the main doors. That's the planner. The low-level part of your brain is just looking at the sidewalk, avoiding the person on a skateboard, and stepping over a puddle. That's the executor.
That two-tier agentic system is precisely how Qwen-Robot Nav is structured. The brain of the operation is an upper-level planner, typically a massive, resource-heavy model like Qwen 3.6+.
Okay.
Its sole responsibility is to take long, complex natural language goals and decompose them into manageable sub-goals. If the prompt is, go find my laptop in the kitchen, the planner breaks that down into, navigate out of the bedroom, find the hallway, turn left at the staircase, and locate the refrigerator.
And the executor handles the pavement, essentially.
Yes. Qwen-Robot Nav acts as the highly reactive ground-level executor. It receives those sub-goals from the planner, consumes the live high-frequency video feed from the robot's cameras, and predicts the immediate physical waypoints.
Like the actual X, Y, and theta coordinates for the chassis to move to in the next half second.
Exactly.
I see the logic, but mechanically, this feels like it should break your hardware.
How so?
Well, if I am the upper-level planner and I am commanding the executor to wander around a massive university building for 20 minutes, processing high-definition video that entire time, the context window of the large language model should explode.
It really should.
Video data is incredibly heavy. You can't just shove 20 minutes of 60 frames per second video into an LLM prompt. Your Raspberry Pi would melt, and even a massive cloud cluster would run out of active memory. How does it not crash?
You hit the nail on the head. The memory bottleneck is the single biggest failure point in embodied navigation. The solution introduced here is what they term a parameterized interface.
A parameterized interface.
Yeah, the upper-level planner doesn't just hand the executor a destination. It dynamically dictates how the executor is allowed to visually consume the world.
Wait, the planner is literally throttling the robot's visual attention span?
Exactly. The planner controls several continuous parameters on the fly. The most critical one is the visual token budget, which it can dynamically adjust between 2048 and 4096 tokens.
Let's break down a visual token for the listener. What does it actually mean to limit the budget?
So an image fed into an LLM is chopped up into small patches, or tokens. If the planner sets a low token budget, the executor model is forced to heavily compress the incoming video feed.
It gets blurry.
It loses fine detail, yes, but it saves massive amounts of compute. If the robot is just walking down a long, empty hallway, it doesn't need high-definition textures of the drywall.
Yeah.
Planner drops the budget.
That makes total sense.
But if the robot is told to find a specific set of keys dropped somewhere on a cluttered rug, the planner maximizes the token budget, allowing the executor to analyze the high-resolution details of the floor.
So it changes its visual acuity based on the task.
Yeah.
But what about memory? How does it clear out the old video so the context window doesn't fill up?
The planner manages that through a parameter called temporal decay.
Temporal decay.
It dictates how quickly the executor forgets the past. If the robot is tracking a fast-moving target, the planner cranks up the temporal decay. The model focuses entirely on the frames from the last 2 seconds and aggressively drops older frames from its memory, keeping the compute incredibly light.
But if it's exploring a new room looking for an object, it lowers the temporal decay, forcing the executor to hold a longer history of frames so it doesn't act like a goldfish and search the same corner of the room 3 times.
Precisely. And the planner even adjusts camera weights. If the robot is navigating a narrow, straight corridor, the planner can tell the executor to ignore the side-facing and rear-facing cameras entirely, putting 90% of the visual processing power into the front camera.
It is a highly efficient, dynamic resource management system.
It really is.
But even with a dynamically shrinking context window, if a robot is walking around for 20 minutes, it needs some kind of long-term memory. Otherwise, it might leave the kitchen, enter the living room, and completely forget where the kitchen was.
Which is why the system utilizes a 2-level memory architecture. The short-term memory is the video feed managed by the temporal decay. The long-term memory relies on an elegant tool called the evidence notebook.
Oh, I loved this part of the paper. Explain how it logs the environment.
As the robot successfully completes those short sub-goals we mentioned, say navigating from the bedroom to the hallway, it does not store the raw video of that journey. Video is too expensive. Instead, a lightweight harness script runs concurrently, analyzing the video rollout and compressing it into a textual journey summary.
It turns the video into a text log. Like, I walked past the brown leather couch on my left, avoided a glass coffee table, and entered a hallway with a blue rug. Text takes up virtually zero memory compared to gigabytes of video.
Exactly. And while it's walking, the vision system is constantly spotting objects and logging them into the persistent evidence notebook. Let's say the main goal is to find an apple. While navigating the hallway, the robot glances into a side room and spots a refrigerator. It logs. Refrigerator spotted at coordinates XY semantic tags. Kitchen, cold storage, food.
It logs it, even though it wasn't looking for it.
Yes. 15 minutes later, the robot is still searching for the apple. The upper-level planner queries the evidence notebook, reads the text logs and reasons. Apples are usually in refrigerators. We saw a refrigerator at coordinates XY. Let's set a new sub-goal to navigate back there.
That is incredibly sophisticated spatial reasoning, and they prove this works in the real world. For the students listening, picture this. The researchers loaded this exact software onto a Unitree Go-To robot dog. It's a quadruped, and they dropped it into a massive multi-room exhibition hall.
And we really must emphasize this was an out-of-distribution environment. The robot had never seen this building in its training data. It didn't have a preloaded GPS map. It had no internal 3D scan of the walls.
Zero prior knowledge.
None.
And they just gave it a pure natural language instruction. Navigate from the living room area to the medical room. The medical room was 21.78 meters away. For an indoor robot relying purely on an onboard camera and an LLM, 21 meters is a marathon.
It's massive.
Yeah.
But it accomplished the task entirely through visual grounding. As it walked, it read the environment just as a human would. It recognized the semantic meaning of different furniture clusters to identify the living room. It read overhead signage to confirm the direction of the medical room.
Wow.
It managed its token budgets, updated its evidence notebook, and traversed the entire distance.
It's a brilliant deployment, but my student brain immediately spots a potential flaw in the training.
Let's hear it.
If the planner is constantly changing all these variables, sometimes giving the model 4,000 tokens, sometimes 2,000, sometimes a heavy temporal decay, sometimes light, how does the executor neural network not just completely overfit and break? If you train a model to expect 4,000 tokens of high-def detail, and the planner suddenly starves it down to 2,000 tokens, shouldn't the model crash?
You're touching on a core principle of robustness called domain randomization. The researchers anticipated exactly that failure mode. They solved it through aggressive training time randomization.
How aggressive are we talking?
Complete randomization. During the training phase, every single continuous control parameter, the token budget, the temporal decay rate, the camera weights, is randomly scrambled at every single step of the process.
So 1 second, the training model is looking at the world with a massive memory and high-definition vision, and literally the next second, it's practically blind and has amnesia.
Yes. The model never once trains at a fixed, comfortable setting. It is constantly thrown into a combinatorial blender of different constraints.
And that forces the neural pathways to generalize.
Exactly. Because it was never allowed to overfit to one specific token budget or one specific camera angle during training, it is entirely unfazed when your capstone planner dynamically shifts those parameters in the real world.
That is just bulletproof engineering. Okay, so let's check our roadmap. We have the hands sorted out with Qwen-Robot Suite. It's dexterous and persistent. We have the legs and eyes sorted out with Qwen-Robot Nav. It can manage its own visual memory and traverse a building to find what it needs. But we have to address the elephant in the room.
Let's do it.
The absolute biggest fear you have as a first-year robotics student sitting there with your Raspberry Pi.
Fisher of hardware destruction.
Exactly. You are a student. You are learning. You are going to write bad Python code. You are going to make a sloppy CAD model with the wrong center of gravity. And if you deploy an untested experimental policy directly onto a $10,000 robotic arm in the university lab, and your bad code tells the arm to accelerate downward through the solid metal workbench,
The arm will destroy itself.
and you will be having a very uncomfortable conversation with your department head. You need a safe place to fail.
You really need a simulator. But a standard physics engine like MuJoCo or PyBullet isn't enough anymore. Those engines calculate rigid body dynamics, but they don't understand the semantic complexities of vision and language. You need the robot to possess a fully integrated imagination.
And that brings us to the final paper, the final pillar of this ecosystem, Qwen-Robot World. We are entering the imagination.
The central concept here is the language-conditioned video world model. To make this actionable for the students, we need to clearly define what a world model mathematically represents.
Okay.
A world model is a system that predicts the future visual state of an environment, given the current state and a specific action. The classic formulation is state t plus 1 equals a function of state t and action t.
Let's pull that out of the textbook. State T is the present moment. Action T is the movement I am about to make. State T plus 1 is the immediate future. It is exactly how the human imagination works. If you close your eyes and imagine yourself holding a coffee mug, and then you imagine yourself aggressively swiping your hand to the right, you don't need to physically perform the action to know what happens.
Right, your brain's internal physics engine knows.
It knows the mug will fly off the table, the liquid will arc through the air, and gravity will pull it to the floor. You predict state T plus 1 effortlessly. Qwen-Robot World does this, but it generates high-definition photorealistic video to show you its imagination.
And the most profound design choice the Keen team made is the interface they chose for Action T. They explicitly rejected using motor torques, joint angles, or end effector coordinates as the input for the action. They chose natural language.
Language as the universal controller.
Exactly. Consider the physical limitations of joint angles. If your simulator uses a 7-degree of freedom input, it is forever locked to simulating a 7-degree of freedom robot.
Yeah.
But natural language is completely embodiment agnostic. The textual command, pick up the pink bottle, is a universal intent. It works perfectly whether the model is imagining a human hand picking it up, a Franca parallel jaw gripper, or a Boston Dynamics humanoid.
So as a student, you can just type the prompt, pick up the pink bottle, Feed the model a starting photograph of your lab bench, and the model literally hallucinates a video of the robot completing the action, governed by realistic physics.
Yes.
How does the underlying architecture even process that without breaking down?
They utilize a highly complex architecture called a double-stream MMDIT,
Okay.
which is a multimodal diffusion transformer integrated with MLLM action encoding.
More acronym soup.
Hmm?
Let's break down the double stream MMDIT. We have two rivers of data again.
Yes. Picture a massive 60-layer neural network. Down one stream flows the semantic data, the meaning of your text prompt, and the semantic understanding of the initial image. This stream is processed by a frozen Qwen 2.5 VL model.
Okay.
Down the second stream flows the visual generation data, the actual pixels that will make up the future video frames. This is handled by a video VAE or variational autoencoder.
Stop right there. What is a VAE doing in this stream?
A variational autoencoder is a compression tool. Generating raw, uncompressed video pixel by pixel is computationally impossible. The VAE takes the visual data, compresses it down into a dense, abstract mathematical representation called a latent space.
Okay, so it makes it smaller.
Right. It allows the diffusion process to do its work in that highly efficient latent space, and then the VAE decodes it back into visible pixels at the end.
Okay, so the semantic stream understands the prompt, and the visual stream is rendering the pixels. How do they communicate?
Through joint attention mechanisms at every single one of those 60 layers. The semantic stream acts as a strict supervisor, constantly guiding and correcting the visual stream.
Fascinating.
And the brilliance of using the massive Qwen 2.5 VL model as the action encoder is the depth of its internalized world knowledge. Because it has read the internet, it implicitly knows that a robotic arm is constructed of rigid metal. It knows that metal links have fixed lengths, and that hinge joints have physical limits.
Oh. This solves the melting arm problem. If anyone listening has played with early AI video generators like Sora or Runway, you know they hallucinate constantly. A person walks behind a street lamp and emerges on the other side as a bicycle. Or someone reaches for a cup and suddenly their hand sprouts 7 melting fingers that fuse into the table.
Without semantic grounding, video models are just probabilistically predicting pixel patterns. They have no concept of object permanence or material strength.
They just guess what looks pretty.
Exactly. But because Qwen-Robot World uses the MLLM's deep semantic knowledge as a rigid constraint, it physically forces the video generation stream to respect the structural integrity of the robot. The semantic stream overrides the pixel prediction and says, no, this object is made of aluminum, it cannot melt, it cannot stretch.
It enforces physics. But knowing that aluminum is rigid is one thing. Knowing exactly how 20 different robot embodiments interact with 500 different physical objects requires data. Where did they find the training data to teach a neural network how to imagine accurate contact physics?
They couldn't find it, so they built it.
They built it.
They created the Embodied World Knowledge Dataset, the EWK. The scale is staggering. It contains 8.6 million video text pairs, comprising over 200 million individual frames of robotic and human interaction video.
200 million frames. But, just throwing raw video at the model isn't enough to teach it physics. If the model is going to learn the precise causal relationship between a language command and a physical outcome, the text captions attached to those 8.6 million videos have to be obsessively detailed. If the caption just says, "robot moves cup," the model learns nothing about velocity, grip strength, or friction.
You've identified the core bottleneck of world modeling. The quality of the simulated physics is entirely dictated by the quality of the annotations. To solve this, the researchers architected a hierarchical 5-layer annotation pipeline.
A 5-layer pipeline.
They didn't just label the videos, they built a structured chain of thought process to extract the physics.
Walk me through how a video of a robot picking up an apple actually gets annotated through this pipeline. What does it look like mechanically?
It starts macro and drills down to the micro. Layer 1 extracts the task goal. The annotator model looks at the video and infers the high-level intent. The goal is to move the red apple from the counter to the wooden bowl.
Okay, that's standard. What does layer 2 do?
Layer 2 isolates the action detail. This strips away the intent and focuses purely on the spatiotemporal mechanics. The right manipulator arm approaches from the axis at 0.5 meters per second. The parallel jaw gripper closes with moderate force on the lateral sides of the apple.
Wow, it's mapping the exact kinematics. But how does it know the apple was actually picked up?
That is layer 3 physical feedback. This is arguably the most crucial layer for a world model because it explicitly maps the state T+1 transition. It describes the observable physical consequences of the action.
Give me an example.
The apple is displaced upwards. The gripper surfaces make secure contact without deforming the apple. The wooden bowl shifts slightly upon the apple's release.
So if you skip layer 3, the AI imagines the gripper closing, but it doesn't know if the apple squishes, slips, or successfully lifts.
Exactly. Layer 3 grounds the action in verifiable physics.
And then what?
From those 3 foundational layers, it then generates the final 2. Layer 4 takes all that data and writes a comprehensive description, a dense 100-word paragraph detailing every single aspect of the interaction. And Layer 5 distills it into a concise description, just 15 to 30 words capturing the essential command.
By training on both the dense physics breakdown and the concise human command, the model learns to respond accurately whether you give it a highly technical engineering prompt or just casually say, put the apple in the bowl.
That level of microscopic detail across 8.6 million videos is how it builds an internal physics engine. And this leads directly to a capability that I think is going to be the most utilized tool in your entire capstone project. The paper calls it human-to-robot transfer.
I remember this. It is a profound capability.
It acts as a massive synthetic data engine.
Listen closely to this, everyone. Because the model has learned that natural language is the universal bridge between all physical embodiments, it can translate actions across species.
You really can.
Let's say your capstone project requires your robot to perform a highly complex task, like assembling a gear mechanism. You don't have thousands of hours of data showing your specific robot doing this, but you have your own hands. You can take your smartphone, strap it to your chest or your head, and record an egocentric video, a first-person view of your own human hands assembling the gears. You feed that raw human video into Qwen-Robot world.
The semantic stream of the model analyzes the human video. It understands the physical interactions occurring, the pinch grasp, the torque applied to the gear, the spatial alignment. It translates that human action into its internal universal language representation.
And then it uses its visual generation stream to hallucinate a completely new, physically accurate video. But in this new video, your human hands are gone.
Completely replaced.
They have been perfectly replaced by the metallic grippers of your specific lab robot, performing that exact same gear assembly task. It maintains the physics, it maintains the goal, but it swaps the embodiment.
The implications for training are just massive. If your manipulation policy needs 5,000 video examples of the robot picking up a screwdriver to learn the correct trajectory, you do not need to manually teleoperate the robot 5,000 times in the lab.
Nobody has time for that.
Exactly. You can demonstrate the task yourself 50 times, feed it into the world model, and let the AI synthesize thousands of perfectly accurate training videos of the robot performing the task from different angles and with different lighting. It completely bypasses the physical data collection bottleneck.
It is essentially a cheat code for robotics. But getting an AI to that level of physical intuition isn't easy. How did they train the neural network to possess both the general visual creativity to generate video and the strict, rigorous obedience to Newtonian physics?
They utilized a General Plus Expert Progressive curriculum. It is a carefully staged, 2-part training recipe. First, they train the model purely on general internet video and image data.
The general stage, what is it learning there?
It is learning the baseline rules of visual reality, geometry, lighting, shadows, textures, object permanence, and basic macroscopic dynamics. It learns what a room looks like, how shadows cast across a floor, how a bouncing ball behaves.
But internet videos don't teach you how to apply torque to a bolt.
Exactly. Once the foundation is laid, they shift to the expert stage. They radically alter the data mixture to be 70% embodied data, the dense EWK dataset we discussed, and only 30% general data. And within that 70% embodied chunk, 90% of it is heavily focused exclusively on manipulation data.
Wait, why bias it so heavily toward manipulation? Why not equal parts robot dogs walking and robot arms grabbing?
Because locomotion is visually relatively simple. The background just scrolls past. Manipulation is where the most complex, chaotic physical interactions occur.
Like friction and stuff.
Yes. Contact dynamics, friction coefficients, severe visual occlusion when a hand covers an object, rigid body joint constraints. These intricate laws of physics are best learned by watching hands and grippers manipulate objects at incredibly close range. By overwhelming the model with manipulation data during the expert stage, they inject deep, specialized physics intuition into its general visual priors.
And the proof that this curriculum works is in the benchmarks. The researchers ran Qwen-Robot World through the World Model Bench, which is an evaluation suite designed specifically to test if an AI actually obeys the laws of physics or if it's just making pretty pictures. When Robot World achieved perfect scores on Newton's laws of motion, mass conservation, and fluid dynamics.
It fundamentally understands gravity. It understands spatial boundaries. It knows implicitly that you cannot push a solid aluminum block through a solid wooden table. It refuses to generate a video where that happens.
Hmm?
It has built an implicit physics engine purely through observing language-conditioned video data.
Okay, let's pull all of this dense theory back down to Earth. You are sitting at your lab bench. You've got your Pi, your servos, and your CAD files. And now you have the full blueprint. You understand the why and the how behind the curriculum your professors handed you.
You understand the three interconnected pillars of your capstone.
First, you have Qwen-Robot Manip. This gives your robot dexterous hands. It teaches you that aligning the data to a universal visual space matters far more than just scaling up raw numbers. It gives your system the ability to adapt to your slightly warped 3D printed brackets on the fly, and it gives the robot the emergent human-like persistence to retry a task when it drops a resistor.
Second, you have Qwen-Robot Nav. This gives your robot spatial awareness and mobility. It reframes movement not as a motor problem, but as an observation context problem. It teaches you how to dynamically manage visual memory and attention spans over long distances using tools like the text-based evidence notebook to explore entirely unseen environments without crashing your computer's RAM.
And finally, you have Qwen-Robot World, the imagination. The safe space. It gives you a language-conditioned physics simulator where you can test your untested policies, synthesize thousands of training videos from your own human movements, and ensure your code obeys the laws of physics before you ever risk flipping the power switch on that $10,000 robotic arm. You have the theoretical meat. The syllabus is over. You are ready to start building.
It is a remarkable, cohesive ecosystem to be learning on. Unifying perception, action, and simulation for the common interface of natural language represents a massive leap forward for the field of embodied intelligence.
But as we wrap up this deep dive, I want to leave you with one final provocative thought to mull over while you're stripping those wires before your next class. We've established over the last hour that natural language English mostly is the ultimate universal interface to teach these robots physics and actions.
It perfectly bridges the gap between human intent and robotic execution.
But as these world models simulate increasingly complex, high-speed, multi-agent robotic dynamics, things that happen in milliseconds, contact physics that human eyes can barely even track, will the AI eventually find human language too slow, too imprecise? As your capstone robot learns, adapts, and imagines its physical reality, will it eventually hit a bottleneck where English just isn't descriptive enough? Will it need to invent its own high-density mathematical physical dialect to accurately describe the world it's navigating, leaving our language behind entirely?
As we push the computational boundaries of embodied intelligence, the limitations of human vocabulary may very well become the next great hurdle. It is a fascinating possibility.
Something to keep in the back of your mind when you finally compile your code. We wish you the absolute best of luck on your 2-year robotics journey. The lab is officially open. It's going to be a wild ride.